Hey everybody, welcome to Physics After Hours. This is a new thing I'm trying where I'm working through some problems, either homework, test problems, examples we did in class, and I'm going to videotape it so that you can watch them later and pause where you need to and start playing again. I know several of you have requested this. So I hope you find this useful. Please tell me if it is in fact useful, because it takes kind of a long time to make. So I want to make sure people are getting use out of it. I want to start the first session with the Unit 1 test solutions. And this is for the Tuesday and Thursday class. If you're in the Monday, Wednesday, Friday class, still watch this. The tests are very similar, so you should try to get all the practice you can get. Okay, starting with the exam, and I do apologize that I have to be kind of zoomed in. I can't get the entire page into the picture because the resolution suffers when I do. So I'm going to have to be somewhat tight in on the paper. Okay, so a few things I wanted to point out where, of course, you had the grading scale. I tried to break it into categories, mostly so that I can give you some points, just for setting up the problem, and so you know how important it is to set up the problem correctly, draw a diagram, fill in the chart, all that kind of stuff. I would note that within these categories, I am somewhat, there is somewhat of a subjective nature to it. So, for example, correctly listing all your forces is worth 4 points. If it's something that's just going on in the y dimension and you don't include one of the forces in the x direction, I didn't count off points for that because it wasn't particularly germane to the problem at hand. Whereas if you left off one of the forces in the y direction, that threw your whole problem off, and so I counted off points for that. Basically, I wanted to see that you understood how to do this. If I believed you knew how to do correctly list your forces, you got full credit. If you didn't know, you got somewhere in between 0 and 4, depending on what your level of communicating your understanding was. Okay, so if we can move on, I'd like to talk about these graphs first. This is a really important thing that I really hope you understand how to read a graph of motion. The problem asks us which one shows an object that comes to a stop at the end of the measurement period. All right. So what does come to a stop mean? Well, that means velocity equals 0. And how do we get velocity from the position graph? Well, we know velocity equals the derivative of x with respect to t. But average velocity equals change in x over change in t. And you can kind of just think of average velocity for a little bit, because the average velocity is going to equal slope for a linear x of t. So for example, let's look at this problem right here. Well, you have x initial and you have x final, and that's going to be negative because delta x is final minus initial, x final minus x initial. So it's going to be a negative something over delta t, and that will equal the average velocity. So the velocity is given by the slope of this line, and it's a linear graph, so it has a constant slope, and therefore it has a constant velocity. At no point does this velocity equal 0. The position equals 0 when it crosses the axis here, but its slope is the same throughout, so it has a constant velocity. Now let's look at another simple equation with a simple chart with a linear line. In this case, we have x final, x initial are exactly the same. The object is not moving at all. It is staying at one position, x, at all time. So this object is at rest, but it did not come to a stop. It was at rest the entire time. It was just not moving at all. All right, so those are the simple cases. Now, if we have a curved graph, like, I don't know, a simple quadratic, where this is time and this is x, we can't simply look at the average velocity or the change in x over change in t. We have to look at the derivative to give us an instantaneous velocity. And what that derivative gives us is the slope of the tangent line. The tangent line, well, I'll just put dx dt equals slope of tangent line. I hope I spelled tangent right. Maybe that's too simple. So this is giving the instantaneous velocity at any point in time t. At a later time t, the slope is going to be much higher, right? Because the tangent line is over here, the tangent line being the line that only intersects the curve at one point. So it's right there. That slope is much lower, so its velocity is very low here. So if you think about this, the slope of this line is changing all throughout time. We get the derivative gives us the slope at any point in time. Okay, so back to the problem here. The object is coming to a stop at the end of the measurement period. So that means that velocity must equal 0, as we said here, and slope must equal 0. Or in the instantaneous case, it's the slope of the tangent line. So in this case, this is a perfect example of an object that is at rest, but it starts at rest, and then it speeds up, and its speed gets faster and faster. And we already addressed these two. Here is an object that starts with some velocity. You see it has the slope of the tangent line. It slows down later, so at point t, this is the velocity. And then at the very end of the measurement period, the slope is 0. The object is at rest. It came to a stop at the end of the measurement period. So the answer is D. Number 4. If you want to look at the next graph, this shows an object that starts at 0 slope or velocity equals 0 and then speeds up in the negative direction. And it also does not start at the origin. It starts at some distance, delta x, away from the origin. Okay? So moving on, what is the relationship between instantaneous speed and instantaneous velocity? Well, speed and velocity are not identical. Instantaneous speed is the rate at which instantaneous velocity is changed. Nope, that's instantaneous acceleration. So this is out. Instantaneous speed is the magnitude of instantaneous velocity. This is the right answer. Velocity is a vector that has magnitude and direction, and speed is a scalar, just magnitude. Of course they're related. That's not a good option. And instantaneous speed is initial speed minus final speed. Actually, that's well, no, we're talking about speed, not velocity. If this were velocity, that would be average acceleration. But this is actually nothing. All right. A particle moves on the x-axis. When its acceleration is positive and increasing, its velocity must be positive. Well, what would the acceleration have to do with the velocity? The acceleration changes the velocity, but it has no constraint. It does not say because you have a positive acceleration, you have to have a positive velocity, or vice versa. So it has no constraint on there, and so both of these are out. The perfect example is projectile motion. You throw a rock into the air, it goes up, it comes down. It starts with v0, it ends up with negative v0, but its acceleration this whole time is one direction. So you have the same object can have velocities in different directions, all being acted upon by the same acceleration. So none of these can be right. Okay, so let's just think about the situation when you have a positive acceleration. And so we'll call this in the positive direction of y. And let's assume that we have positive velocity, initial velocity. Well, as you start up, you're going to get faster and faster and faster. I'm going to show a little arrow that gets bigger and bigger. That shows increasing velocity because your velocity is in the same direction as the acceleration. Well, if your acceleration is positive and your initial velocity is negative, what you're going to have is this v0 that gets smaller and smaller until v equals 0. Then it's going to come back and start getting larger and larger and larger. Just like it's like the inverse of projectile motion. The object's coming down, slowing down, stopping, and then speeding up in the different direction. So in either of these cases, of course, key word here being must, you cannot say that it must be slowing down, and you cannot say that it must be speeding up, because it could be doing both in one trip, right? Because if it's going in the opposite direction of acceleration, it's slowing down. If it's going in the same direction as the acceleration, it's speeding up. So when acceleration, well, let's keep it negative. When acceleration is negative and velocity is negative, speeding up. When acceleration is negative and velocity is positive, slowing down. All right, so none of the above must be true. All right, so here's our classic projectile motion problem. The stone is thrown horizontally and follows the path XYZ as shown. The direction of the acceleration of the stone at point X is, the acceleration at point X is, well, it's down. It's always down. Because the acceleration equals just the acceleration in the Y direction. Acceleration in the X direction equals 0. So it's down. A force of 1 Newton is, well, you know that force net equals mass times acceleration. That's Newton's second law. Forces in units of newtons, that equals kilograms times meters per second squared, which is acceleration. So kilogram meters per second squared. I think 100% of the people got that question right. All right. This graph shows the position of a particle as a function of time. What is the velocity between t equals 5 and t equals 9 seconds? Well, in this case, we can say A acceleration is constant. Why? Because the line is linear. The curve is linear. So I'm sorry, I'm sorry, it's just velocity is constant, excuse me. Velocity is constant because the graph of position over time is linear. We can also say, because it is linear, the average velocity is equal to the instantaneous velocity. In other words, the average velocity, which is delta x over delta t, is equal to the linear velocity, which is dx over dt. So we're not going to have to worry about derivatives. All we're going to have to compute is v equals v average equals d delta x over delta t, which is the same thing as saying the slope. So if the graph, the curve of the graph equals the slope, you know, because it's a linear line, then you can say the instantaneous velocity equals the average velocity. All right, so the x initial equals 12 meters, and the x final equals 0 meters. That is delta x. Delta t is our t final over here equals 9 seconds, and our t initial equals 5 seconds. Okay, so putting that into the equation, velocity equals delta x over delta t equals x final minus x initial over t final minus t initial, because delta is always final minus initial. That's all this delta means. This equals 0 meters minus 12 meters over 9 seconds minus 5 seconds equals negative 12 over 4 meters per second. So velocity equals negative 3 meters per second. Okay? Next. Okay, so this is the derivative question. You had the same problem as my other class did, and while recording their solutions, I had some trouble with the document camera stopping recording and all this kind of stuff. So I'm going to go back later and record this problem, and then you can both use it, because it's the same problem in both classes. So going on to problem 8. All right. I'm going to switch to pencil here because it's always better to work with pencil. I was trying to show more contrast and vivid color, but I like being able to erase too much. A rock is thrown straight up with an initial velocity of 15 meters per second. That's v0. What time interval elapses between the rock being thrown and its return to its original launch point? So time interval, t, is what we're after. Find t, and it returns to its original launch point. That's very important. So let's fill in our variables. You know, these are all 0. If you wanted to, you could just put an x through there to indicate that the motion is only along the y direction. That's fine. Y0, well, let's draw our little diagram to give us an idea. Now it's falling back at the same position. I spread this out in X just to, you know, explode the diagram a little bit so you can see what's going on. So this is V0. This is negative V0. Y0 and Y. Okay. So we know Y0 is 0. Why is it 0? Because we can call any point we want the origin. Why not call it one of these important points? That makes all of our problems so much easier. Well, y is the same point as the launch point, so it is also 0. The y0 is plus 15.0 meters per second, and Vy, these are y, equals negative 15.0 meters per second. How do we know this? We know this from symmetry. the object is just acted upon by constant velocity, so the time it takes to go up is the same as the time it takes to go down. So its deceleration on the way up is going to equal, in magnitude, its acceleration on the way down. So the magnitude, the velocity here and here are going to be the same, just different signs. Now, if you didn't notice that, that's okay. I didn't count off points for that because you can solve the problem without having to have that. And that's actually what I'm going to do right here for you now. Is I'm not even going to use that. So the acceleration we know is always negative 9.8 meters per second squared. And t equals ty. It's just a formality with the time. So if we look at the equations given to us, we need to find something that's going to have time in it. So this one's out. We don't know what, well, we do know what the final velocity is, so we can find it that way. We can also, we can't do this because we don't know what the height is. Well, actually we do. It's coming back to the same position, but it's going to be, you're going to end up with a 0 equals 0 equation. So let's not use that. Let's start off with the second equation. For some reason, that's the equation I always run to. So y minus y0, all I did was change the change from x to y, equals v0y t plus 1/2 ay t squared. Okay. These are both equal to 0. I'm actually going to scoot this over here. Okay, so I'll have room over here to do something else. So 0 equals v0yt plus 1/2 ayt squared equals, factor out the t, v0y plus 1/2 ayt. Okay, so now you have possible two solutions. Either t equals 0, which is okay, mathematically it's a correct solution, but physically it doesn't make sense because you're looking at the time it takes to go up and then come back down. 0 is just a time at which the object's going to be at that point, which of course you know it is at the beginning, but you don't learn anything from that. Or v0y, or v0y plus 1/2 ayt equals 0. To do it a different way, maybe you don't like me doing it that way, so let's just do it explicitly by saying y plus 1/2 ayt and divide each side by t. Well, 0 divided by t is 0, and t divided by t is 1, so 0 equals v0y plus 1/2 ayt. All right, we're going to subtract v0y from each side. So negative v0y equals 1/2 ayt. We're going to multiply each side by 2. 2 times 1/2 is 1. And 2 over here is just negative 2. v0y equals ayt. Divide each side by ay. And I'm going to flip the equation too, so you have the unknown on the left. It's negative 2 v0y over ay. That's our solution. And further, t is negative 2 times 15 meters per second over negative 9.8 meters per second squared. I don't remember what this is. This is, let's see, 30 divided by, so it should be, I think, what was it, like 3.06 seconds, I think? I think that was it. That is one way to work it. A second way to work it, equally valid, was we use that equation that says Vy equals V0y plus AYT. Okay. Well, because we did this thing up here, we know what the final velocity is. And we know that, well, actually I wrote this symmetry here. This is just negative Vy0, right? So or v0y, however you want to write that. So I can insert that in for vy. I have negative v0y equals v0y plus a sub yt. Subtract v0y from each side. You probably see where this is going. This minus this equals 0, and this minus this is negative 2 v0y equals ayt. Oops. Okay. And I'm going to divide each side by ay, and I'm going to flip it. Negative 2 v0y over ay. Look, we have the same solution. Doesn't matter which way you work it, it's the same solution. There is another possibility for working this problem. I thought it was maybe a little bit more complicated, so I didn't want to work it that way, but I think several of you did. If you did it correctly, it was perfectly fine. I gave you full credit. If you obviously did not do it correctly, I did not give you full credit. But the point is, some of you, let me position myself correctly. Some of you work the problem by saying, I want to see the time it goes up to the peak. At that point, Vy equals 0. And of course you have V0y down here. So, and y0 and y. So listing your variables, you have y0 equals 0, y equals we don't know, v0y equals, what was it, 15 meters per second, vy equals 0 now because we're at the peak. This is the point at which it stops, and an instantaneous moment later it starts speeding up in the opposite direction again. Ay equals negative 9.8 meters per second. Ty equals tx equals t. Okay, so at this point we can just go to the simplest equation then. Vy equals v0y plus at, and now we know this equals 0. v0y we have, we just need to solve for t. So minus at, if we subtract at from each side, we have negative a over t equals v0y. Divide by negative a, divide by negative a. T equals negative v0y over a, and that's ay. So put out those subscripts. Okay, so that's kind of your solution there, except that if you note over here, notice this is 1/2 of this. In order to solve the problem this way, you have to recognize the symmetry. That, let's call this T1, or we actually called that T. So call this T, then this is T2, and T, I don't know, total equals T plus T2. And T equals T2, so T total equals 2 times T, right? So if we say T total equals 2T equals negative 2 V0y over delta y, and that then is equivalent. But the point is, you have to say that the time up is equal to the time down, so you just double it. All right. Moving along, I guess we have 2 more. Okay, we're to the force problems. Let me adjust this. Okay. All right, so a 25 Newton crate, that is Fg. Just refocusing here. Okay, guess that's as good as it gets. Slides down a frictionless incline that is 25 degrees above the horizontal, that is theta, with constant velocity, that means ax equals 0. Find the magnitude of the normal force on the incline on the crate. Okay, I'm going to write down my knowns. FG is equal to 25 newtons. Theta equals 25 degrees. AX equals 0. And that's all we know. So now I'm going to draw a diagram. Well, this is just a sketch. Oops, sorry, wrong. Thinking of the wrong problem. We're on an inclined plane at angle theta. At FG, we have the normal force that is normal to the plane. Normal is math speak for perpendicular. Normal and perpendicular mean the same thing. So that's why we're talking about the normal force being perpendicular. And we have gravity, and that's all that's mentioned. We don't have friction. We don't have anything like that. The important thing here is labeling theta correctly. Theta is equal to the incline, the angle of elevation of the incline, because we defined this as theta. So when we search for theta over here, we make the point of knowing this angle equals that angle. Now, a lot of times people want to like draw the x component of the gravity and then say they'll identify this as theta. That's wrong, and I'll show you why. If, let's say, we have some angle, some elevation, and the elevation gets greater and greater so that it's a very large angle of elevation, and that is theta. We draw our block, we draw our gravity, and we draw the opposite of the normal force. Now that angle is really large, whereas this angle down the plane is really small. If we draw a shallow elevation and theta is very small, then this angle is very small too, whereas this angle here is huge. So this angle cannot equal theta. It must be this one over here. And of course, if we were to flip the incline, everything would be different. But I'm sure you get that. All right, so now I'm drawing my free body diagram. The free body diagram is the one in which the object in question is represented by a point, and all forces emanate out from that point. So that is the force of gravity at angle theta again. This is the normal force. The important thing to note here is that if you have an incline, you have to shift the axis to correspond to that incline. Well, why is you can draw your axes however the heck you want to draw them. You can draw them in any kooky way you can think of, but you want to draw the axes in a way that makes your problem easier, right? I mean, that's the whole point. And so just trust me on this. If you angle your axis so that the x direction is along the motion on the plane, everything's going to be much easier. Now, of course, by this point, I hope that you recognize that we have a right triangle here, and this is FGY, and this is FGX, which is the same as drawing FGX up here. Now the question could arise, why did I draw that right triangle like that? Why didn't I draw it here and make this my 90-degree angle? Well, that's not going to be too terribly sensible because, just drawing my right triangle, if you remember, whenever we're drawing vectors, you have a resultant vector that is always the hypotenuse. You're either taking two vectors and adding them, two perpendicular vectors, and adding them to get the resultant, or you're taking the resultant and breaking it down into perpendiculars. Sorry, that's FG. But the vector, the overall vector that's going to be broken down is the hypotenuse. And then your perpendicular vectors are going to be FG or FY. So if I were to draw some angle that was like, some triangle that was like this over here, like I started to draw with that being the right angle, now all of a sudden FGY, sorry, FGY, FGY, FGX. Now all of a sudden FGY is the hypotenuse. That's no good. And FG would be the leg of the right triangle. That's no good. So your vector that you're breaking down is always the hypotenuse of the right triangle that you draw. Okay, now what I like to do is draw another free body diagram in which I just have parallel and perpendicular components so that I can add everything up easily. You have FGY, you have FGX, and you have the normal force. I took this vector and broke it down into its two components and put them on this graph. That's all I did. Put that in blue. So you can't mix up these components with the vector itself because you're breaking this down into these blue components. So once you break it down, you can't mix them up. So that's kind of why I like to draw this separate diagram with the post-broken down vectors. All right. Now comes the point where we sum up our vectors. We have in the x direction just FGX. I'm sorry, let me go back. Let me break this down further. So FGY equals what? Well, it's going to equal FG cosine of theta. And FGX is going to be equal to FG sine of theta. Why is that? Well, we have a right triangle, and we have, if you remember like from before with Pythagorean theorem, ABC, where C is the hypotenuse. But in this case, and we have the angle theta, in this case we're going to have F, G, and let me erase those. FGY and FGX. All right, and put that box there. You know, sine of theta, and this is the definition of sine of theta. Sa, ka, to, sine of theta is equal to the opposite over the hypotenuse. So in this case, sine of theta equals FGX over the hypotenuse FG. Multiply G times each, FG times each side. You have FGX equals FG sine of theta. And that is what we did there. Similarly, cosine of theta equals adjacent over the hypotenuse. So cosine of theta equals the adjacent, which is FGY. That means it's right next to the angle, over FG. So FGY equals FG cosine of theta. And that is what we have over here. So just simple trig relations. If you are having trouble with this, you definitely need to go back and review this because it's going to be such a big part of our course. All right, summing up the forces, and I really wish I could get the whole document in the viewfinder here, but unfortunately the resolution is just terrible if I do that, and it won't allow me to zoom in and out, so we'll just have to deal with it. In the x direction, we have positive FGX, which equals positive FG sine of theta. I'll go back to the diagram here. Remember, in the x direction, we just have this one component. In the y direction, we have positive normal force, but we have a negative FGY, which is GY, which is equal to negative FG cosine of theta. The negative comes because it's in the opposite direction. Going back to the diagram, Fn and the negative Fg cosine theta. They both work in the y direction. Okay, so back to the chart. This problem states that the crate is moving with constant velocity, so the sum of the forces, we would say, because the acceleration is 0, we would say the sum of those forces equals max, as it always does, Newton's second law, and we would circle 0. Now, some of you, or one of you at least, question this, that we only have one force. How can there not be a net force greater than 0? Okay, that's a very astute observation, and basically I'm just going to say that there's some mysterious force that the problem doesn't mention, that you're right, has to be there to balance out the forces and equal 0 acceleration. This is one of those situations that arise when I take a problem and mix it up by changing the numbers or something. The thing is, it's not going to affect us because we're only going to deal with the sum of the forces in the y direction. Okay, so let's sum up all of our forces, and I will do the x direction. So Fg sine of theta, that's the only force, and that equals max, which equals 0. Okay, we're not going to use the sum of the forces in the x direction. I think if you didn't sum that, I didn't count off points, or maybe, oh gosh, I can't remember if it did, it was a small amount of points. It's not needed for this problem, but it is definitely necessary that you get in the habit of summing up all the forces on all sides, just because all I have to do is make the problem a little bit more complicated, and if you aren't in the habit of summing up x and summing up y, you may miss the problem. So let's look at the sum of the forces in the y direction. That equals Fn and negative Fg cosine of theta, which is just negative Fgy. And we know that is equal to 0 because the object is not sinking into the plane and it's not levitating off of the plane either. So the sum of the forces has to equal 0. And then we can just, well, you know, we had no direction in which we were going in this problem. We were just following protocol. But now the solution has presented itself, right? 0, we are solving for Fn. Fn just equals Fg cosine of theta. All I did was add Fg cosine of theta to each side of the equation here. So now we can plug in Fn equals 25 newtons times cosine of 25 degrees. I don't remember what that comes out to. It's got to be less than 25, but it's got to be cosine. Cosine of 0 is 1, and this is a pretty small angle, so it's going to be like something, I don't know, was it around 15 newtons or something? I don't remember. I don't have my calculator with me, and I don't have the key either. But that's your answer. Right, we've got one more problem to go. Hope that the recorder does not flip out on me and stop before I can finish this. We have a 40 Newton horizontal force. That's force applied. We have a 60 Newton block. That's Fg. At rest, so acceleration equals 0 on a rough horizontal surface. If the coefficient of frictions are this and this, the magnitude of the frictional force of the block is well, you know, I'm sorry, I take this back. It was initially at rest. Excuse me. So that does not mean acceleration is equal to 0. That means the 0 is equal to 0. So FA equals 40 newtons, FG equals 60 newtons, V0 equals 0, and mu S equals 0.8, mu K equals 0.7. I'm just writing down my knowns. Got a block on the plane. I'm drawing my forces, Fg, Fn, force applied, force of friction. Force of friction always opposes motion, so we know the direction that is in. I can come down now and draw my free body diagram. Fa, all the forces originate at the center of the object in question. If you wanted to combine these two diagrams, because it's a simple case where everything is horizontal, you could do that. I just broke it up. All right, so back in the chart, summing up our x forces, we have Fa, we have negative force of friction. Is it moving? Well, we don't know that yet. We'll find out in a moment. If you forgot to circle this on the test, I didn't count off because it's something you don't know immediately. You have to, that's the point of the problem, is to find out, does it accelerate or not? Well, actually, the point is to find the frictional force. But in order to do that, you're going to have to see if it accelerates or not. So in the y direction, we have the normal force and we have negative force of gravity. All right? And does that sum to 0? Yes, it does, because the object is not sinking or levitating, so all forces have to balance out. Sum of the forces in the x direction equals Fa minus F equals max. We know this is true. We just don't know if that equals 0 or not, or if there's some non-zero acceleration. Some of the forces in the y direction are Fn minus Fg equals 0. So then we can say the normal force equals Fg. Now, can you get there without doing the summation? Yeah, of course you can. I think a lot of you can reasonably look at this situation and know that the normal force is going to equal the weight. Okay, but the reason we did this was because if I were to make it a little more complicated by just adding a force at an angle there, well, that force is going to have a y component that is going to add in the same direction as the weight, which means the normal force must counter both of those. So you would have to do a summation here, and it would be absolutely necessary. Of course, as I showed you in the points breakdown, it's always going to be necessary to me for grading purposes to do the summation, because I want you to get in the good habit of summing these things up rather than just, looking at it and say, normal force equals weight. Because at some point you're going to be wrong. I think even in your homework you had a problem like that. Okay, so we proved that the normal force equals the weight. But right now we need to determine if there is motion. Now the critical case here, the important point is the maximum force of static friction, which equals mu s times the normal force. We know now that equals mu s times the weight. That is the force you have to overcome in order to start this block from moving. Sorry, I'm beating on the table and it's vibrating. So let's see what that is. Mu s equals 0.8 times 60 newtons. Oh, what was that? That was 48. Yeah, it equals 48 newtons. So that's very important. So then we have to say, how does this maximum force of static friction compare to the force that we are applying to the block? Because the two are in the same dimension, just different directions. Well, the force applied is less than the force of maximum static friction. So therefore, there is no motion. Okay? So we found the force of the magnitude of the frictional force, right? 48 newtons. No! It is not the force of the frictional force. It is the maximum force that friction can supply. Maximum. But in this case, the friction is not going to supply that maximum force. If you remember that really important graph we went over in the lecture, we have force applied on one side and the force of friction on the other. For a while there, it is linear. So some force 1 is going to create friction force 1. They're going to be equal in magnitude. Force 2 is going to create an equal force 2. When you get up to this point, Fs max, that is the point of which you overcome the frictional force and the object starts to move. Then the force of friction drops down to some standard constant level, and that is the kinetic frictional force. That never happens here because our force applied is less than the force of maximum static friction. So it's going to be like F2 here. And if it's F2, then the frictional force is going to equal F2. So friction equals static friction, but not the maximum static friction. So that is going to just equal Fa. So the force of friction equals 40 newtons. And we have our answer. Okay, well, I hope that helps you out going through the test, and do go through the test and solve the problems. You're going to get a chance to take this test again. For my Tuesday, Thursday class, I'm going to talk about this on Tuesday. So make sure you know how to do all this stuff. And also come back and look at the calculus problem, which I will be recording here shortly. Okay. Good night.